Assalamualaikum. Hi guys. In this video, I'm going to start to talk about significance of the atomic spectra that leads to the ionization energy. For Lyman series, the frequency of the convergence for the spectral lines can be used to find the ionization energy. For example, you have IE, the symbol for ionization energy equals to HV, and the frequency here, I just put it as the infinity. So why I put here the frequency is for infinity value. Let's go to this diagram. We have two sets of series. The first one is Balmer. The second one is Lyman series. If you take a look here, the frequency for the first line of Lyman series is much more greater than the frequency of the first line of Balmer series. So you have here, this is the first line for Balmer. This is the first line for Lyman. This is what we call as convergence limit. If I want to determine the value for the frequency at this point for this line, I just assume the value should be until infinity because a whole lot of line spectrums form here. If you take a look here, for the first line in Balmer series, it is caused by the transition of electrons from third energy level, n equals to 3, to n equals to 2, second energy level. So the second line is, for the green one, is caused by the transition of electron from fourth energy level to second energy level. So the convergence of spectral lines show that the difference between successive energy levels becomes smaller. So that's why the gap becomes smaller with increasing distance of energy levels from the nucleus. This is why we relate the convergence limit with the ionization energy. Ionization energy is defined as minimum energy required to remove 1 mole of electron from 1 mole of gaseous atom or ion. For example, I have atom M here in gaseous phase. So I'm going to remove 1 mole of electron from gaseous M atom to get gaseous ion M, and the delta H here is positive sign because it absorbs energy to remove this electron. So the process in which an electron is removed from an atom is what we call as ionization. The energy required to remove the electron is called ionization energy. So this ionization energy is in positive sign to indicate first ionization energy. Next, the ionization of hydrogen involves the transition of the electron from lowest energy level nearest to the nucleus to the highest energy level. So I'm going to choose the nearest to the nucleus is n equals to 1. So that's why we determine the ground state for hydrogen atom is n equals to 1. And the highest energy level is n equals to infinity. At n equals to infinity, the potential energy of electron is 0. This is because electron is free from the nucleus force of attraction, as the attractive forces has no effect on the electron. So in practice, you should know that it is not possible for the electrons to fall from 8th energy level or beyond. This is because when beyond the 7th energy level, electrons are essentially lost and a positive ion is formed. For example, if I have gaseous hydrogen atom, it will form a positive ion to get H plus in gas phase plus 1 electron. So the energy difference between ground state n equals to 1 of the atom and the excited state that corresponds to the convergence limit of the spectral line of hydrogen is the ionization of energy. So the difference between n equals to 1 and n equals to infinity. When we calculate the energy difference here, this is related to the ionization energy for hydrogen. So let's go to the part where if I want to find the ionization energy using the calculation, based on the concept that I taught you before, we are going to determine the ionization energy for hydrogen atom in Lyman series based on N initial and N final. Let's say that our N1 equals to 1, N2 equals to infinity, so you have to determine the ionization energy in kilojoule per mole. I'm going to determine based on Lyman series, N initial, which will be your ground state, is equal to 1, and N final, which will be the higher energy level, is infinity. So let's go to determine the energy needed for 1 electron. So this is the formula that you are going to use based on Rydberg constant. And you know that the value for RH here is 2.18 exponent negative 18 joule. So I'm going to put the value for Rydberg constant, the value for my N initial and my N final. I will have the value for this to be 1 minus 0. So 0 is for 1 over infinity square. Hence, the value for my energy needed by 1 electron is the same value as Rydberg constant. So this is the energy for 1 electron. However, if I want to calculate the ionization energy is equals to the energy for 1 mole of electron. So we have to calculate based on multiplication of energy for 1 electron times with number of electron in 1 mole. So we have the energy right now from this calculation. So the value for energy of 1 electron is this value. Now we have to determine the number of electron in 1 mole. So based on the mole concept before, you've learned that 1 mole of electron equals to Avogadro's constant. So it will be 6.02 exponent 23 electrons. So I'm going to insert this value to get the final ionization energy, which will be in kilojoule per mole is 1312.4 kilojoule per mole. So this is how you get the ionization energy for hydrogen based on calculation of the concept N1 and N2. But if we want to relate with the ionization energy based on experiment, so I'm going to introduce to you, this is the line spectrum. First line is here, and the second line is here because the bigger gap between them. And after that, I'm going to determine based on this line is the convergence limit straight towards to the left. So the convergence limit is the wavelength or frequency at which the converging spectral lines merge together. This is because the difference between energy level becomes smaller and smaller. So you can see the distance between two different energy levels becomes smaller. Hence, I'm going to conclude here as convergence limit. So, we are going to determine the ionization energy by identifying the wavelength of the convergence point. If you take a look here, I just flip my line spectrum. This is the first line, this is the second line, and this is the convergence limit. So I have to determine the ionization energy based on the wavelength of this convergence point. So let's try do the example 20 to calculate the ionization energy for hydrogen atom when you have in terms of spectrum. So this is the diagram for your line spectrum. You have to take note that this line spectrum is in wave number. So wave number is 1 over lambda. Now we are going to determine where is our first line. The gap is much more larger here, so 8.22 is the wave number for our first line. Hence, towards to the left will be our convergence limit. So I'm going to choose my wave number, which will be 10.97. So this is what I have for my wave number for convergence limit. Hence, from here, I'm going to calculate the delta E. So I use the simplest formula, delta E equals to Hc over lambda. And I have Hc, if I take out, it's times by 1 over lambda. So this is the value for my wave number that I have to insert here. So put all those values for the Planck's constant, speed of light, and last but not least, our wave number. You will have the energy delta E equals to 2.18 exponent negative 18 joule. So to get the ionization energy, we know that this is energy required to remove 1 mole of electron. So I'm going to calculate the energy times with 1 mole of electron, our Avogadro's constant. You will have this value. And finally, in kilojoule per mole is 1312.4. So I hope you can understand the difference when you want to calculate the ionization energy based on concept that you've learned, and initial and end final. Or you can also calculate the ionization energy based on this example, line spectrum. Even though you got two methods, you still got the same value for ionization energy, just like this one or this one. You got the same value for ionization energy. So that's it for this video. Thanks for watching. Bye.